Let's begin with a very quick review of what we talked about in class last time, which was how to create 6 mutually orthogonal vectors that we could use for a 6-dimensional basis vector system using sines and cosines. So I divided the interval from 0 to 2 pi into sixths, and then I graphed these 6 functions, 4 cosines and a sine, and the graphs looked like this, and then I used the graphs to compute values at the 6 places where I divided the interval, and I got the vectors a1, a2, a3, a4, a5, and a6 for my basis vectors. I talked a little bit about how if I used different cosines and sines, it would just give me the same vectors over again, so that there were really only 6 that you needed. Now, today I'm going to do the same trick again, but I'm going to use, I gave you this assignment to create a set of orthogonal basis vectors in 5 dimensions, and today I'm going to start out by going over how you could do that assignment. So I have the same interval from 0 to 2 pi, and I'm going to divide it this time into 5 subintervals. So I basically divided 2 pi by 5, and then I went in steps of 2 pi over 5. Let me draw some vertical line segments, and then I'm going to graph a bunch of sines and cosines. Let me start out by just graphing cosines. I'm not going to use all of these cosines, but let's graph cosine of 0 theta, cosine of 1 theta, cosine of 2 theta, 3 theta, 4 theta, and 5 theta, just to see what they look like, right? Cosine of 0 theta is a constant, so it's that horizontal line. Cosine of theta starts at 1, goes down to -1 in the middle, comes back up to +1. That's one full cycle of the cosine curve. Cosine of 2 theta has 1, 2 full cycles, and cosine of 3 theta goes to 1, 2, 3 full cycles. Cosine of 4 theta goes through 1, 2, 3, 4 full cycles, and cosine of 5 theta goes through 5 full cycles. Now cosine of 5 theta is going to line up with my green vertical lines, so that was the easiest one to draw. And you might be, probably when you did this yourself, you used Desmos or something to draw these functions, and you might be thinking to yourself, well, he's crazy, why is he drawing these by hand? But I had a lot of fun drawing them by hand. I found that it was a really useful effort, and I want to share with you a little bit what I was thinking of that helped me visualize exactly how to draw these by hand. It's a good exercise, I think, in giving you more insight into the way the sines and cosine functions work, which will help you understand what's to follow. So first I actually drew a unit circle, and then I wanted to look at the angles of interest, these angles. And actually, instead of dividing 2 pi into fifths, I divided pi into fifths, and I'm just looking at the top half. And you might be thinking, well, he doesn't need this angle pi over 5. He just needs the second angle and then the fourth angle. But you can see from the symmetry that if I look at the cosines and sines of these angles, they repeat. Here are the cosines of the x-coordinates of those points on the unit circle. You can see that the x-coordinate of this point, cosine of pi over 5, is the opposite of the x-coordinate of this point, cosine of 4 pi over 5. So yeah, it's only this number and this number that I'm actually going to need, but the hint that I gave you in the assignment was the value of cosine of pi over 5. So I'm showing you all of the multiples of pi over 5. And we'll look at the y-coordinates as well later when we look at the sine functions, but for right now let's concern ourselves with the x-coordinates. And there are only 3 values we need. The cosine of 0, which is 1, the cosine of 2 pi over 5, which I'll call high, and the cosine of 4 pi over 5, which I'll call low. So we have 3 values, 1, high, and low, that I'm thinking of when I'm looking at the intersections of these functions with the green line segments. So when I look at the first function, cosine of 0 theta, my numbers are going to be 1, 1, 1, 1, and 1, and that will give me my first vector. And when I look at cosine of 1 theta, my numbers are going to be 1, high, low, low, high, if you see how that works. Now when I tried to draw cosine of 2 theta, I was reflecting on the fact that cosine of 2 theta has twice the frequency, so my intersections with the green lines are going to skip every other one. I'm going to go 1, and I'm going to skip high, and I'm going to go to low. So when I was drawing my picture, I was thinking of skipping high, that would be over here, and then intersecting at the place where low intersects over here on its way down. Then I'm going to skip the second low intersection, skip this one, and come back up and intersect at high. Then I'm going to skip 1, and back on my way down I'm going to hit high again. So I can see the intersections are going to be 1, low, high, high, low. And that's my second vector. And that helped me draw the picture as well. For cosine of 3 theta, I'm going to skip 2. So it's going to be 1, I'm going to skip high and get low on its way back up. And that helped inform how I would draw this first part of the picture. I skip high, I skip low on its way down, and I hit low on its way back up. And so my vector is going to be 1, low, high, high, low. Now, let me pause for a second, and you'll notice that this vector, 1, low, high, high, low, is the same as this vector, 1, low, high, high, low. They are the same thing. And if I continue doing the same thing with cosine of 4 theta, I'm going to actually skip 2. Let's see. No, with cosine of 2 theta, I skipped 1. With cosine of 3 theta, I skipped 2. With cosine of 4 theta, I'm going to skip 3. So it's going to be 1. I'm going to skip 1, 2, 3. And then I get to high. And I skip 1, 2, 3. And I get to low. But skipping 3 in a forward direction is the same as going in backward direction. So it's going to be 1, high, low, low, high. For cosine of 4 theta, 1, high, low, low, high. And you can see that these two are the same. And for cosine of 5 theta, of course, 1, 1, 1, 1, 1. These two are the same. And it turns out that I didn't need any of the last three. I didn't need cosine of 3 theta, 4 theta, or 5 theta. I just needed cosine of 0 theta, 1 theta, and 2 theta. We're going to now be able to ignore everything after cosine 2 theta, and let's move on to the sine functions. Now for the sine functions, I need these y values, and there are only two, because sine of 2 pi over 5 is this number up here, which I'll call a, and sine of 4 pi over 5 is this number, which I'll call b. And again, from symmetry, you're going to see that sine of 6 pi over 5 is negative b. Sine of, let's see, sine of 6 pi over 5 would be down here. Sine of 8 pi over 5 is going to be negative a. And then sine of 10 pi over 5 is going to be 0 again. So when we graph the sine of 1 theta curve, we're going to see that from the circle, we're going to see it's going to go 0 up to a, and then to b on its way down, and so on. Here's my graph, and here are my values: 0, a, b, negative a. And when I graph sine 2 theta, I could use that same trick again of skipping every other one. So I've got 0, b, negative a, negative b. And that informs how I draw the graph. And my values are 0, b, let me point to them, 0, b, a, negative a, negative b. And this is basically it. I can now write my 5 vectors. But before I write them, let's remember we need the values of low and high. High Low you get because I gave you the value of the sine of the cosine of pi over 5. So low is going to be the opposite of that. So I know low is negative square root of 5 plus 1 over 4. High you could get from using, say, a double angle formula. Cosine squared of theta minus sine squared of theta is the same as 2 cosine squared theta minus 1. And if you work out the algebra, you get square root of 5 minus 1 over 4. So given the values of low and high, I can now write my 5 vectors. First vector is 1, 1, 1, 1, 1. The second vector is 1, high, low, low, high. The third vector is 1, low, high, high, low. And you can amuse yourself by just on paper demonstrating to yourself that these are all mutually orthogonal. The fourth vector is going to be 0, A, B, negative A, and the fifth vector is going to be 0, B, negative A, negative B. It just remains to write down what the values of A and B are. And for these values, you're going to have to use the Pythagorean identity that relates the value of a sine to the value of a cosine, and that's a little bit messy, but the numbers come out to be, the simplest way I can see to write them is the square root of 5 plus or minus the square root of 5 over 8 for A and B. So that's my quick summary of the solution to the homework that I assigned last time. But before I leave this share, I want to do a quick review of what we talked about a couple of classes ago, because the concept of the trick of using the dot product to allow us to find the coefficients is going to be very important to understand going forward. And I want to make sure that I've said this one more time. So here's a review of how we use that trick. When we have a basis set where all of the basis vectors are orthogonal, we can use this trick of using a dot product to find an expansion. So the idea is we're given some vector v. We know the vector v. We want to find those numbers, little a1 through little a5, that are the coefficients of our expansion of v in our basis set, vectors capital A sub 1, A sub 2, A sub 3, A sub 4, A sub 5. How do I find the coefficients so that I could express my known vector v in terms of these basis vectors that are all perpendicular? Here's the trick. The trick is if I take v and I take the dot product of v with one of the basis vectors, a sub j, then I could distribute that dot product over this sum, and I could take each of these and find the dot product with a sub j. But I've used j as my dummy variable in this expression, and now I want to express v dotted with a sub j. So j is now representing a specific index. So I need to change the dummy variable to k. So this is now the sum from k equals 1 to 5 of ak, and I dot it with the vector aj. And now I have a sum of 5 dot products, but 4 of them are 0 because all of the basis vectors are orthogonal to each other. And so the sum collapses with the sifting property to a single term, and that term is a sub j times the square magnitude of the basis vector, of the jth basis vector. And then if I take this equation and divide by a sub j squared, then I can solve for the coefficient a sub j that I want. And this is the result that we've been using in our spreadsheets. So I just wanted to give you that quick review. Does anyone have any questions about that review? All right, let me give you an idea of what I want you to do next. You had a project to calculate the coefficients lowercase a. Okay, we had a spreadsheet where I actually gave you these cells that had a set of six-dimensional basis vectors, and using these you calculated their square magnitudes, then you calculated the dot product of this given vector. Using these cells you calculated the dot products of the given vector with every one of the basis vectors, and then divided by the dot products by the square magnitudes, and you calculated the unknown coefficients. I want you to do that for homework with a 12-dimensional set of basis vectors but I want you to make the basis vectors yourself with cosines and sines. So I'm going to do a demonstration now where I make a set of 7-dimensional basis vectors with cosines and sines just to demonstrate how you can do this, and your assignment is to do it on your own with 12. And I will be collecting this for a grade. It's due tomorrow night. So I'm going to, I've shared in the actual assignment, I've shared a Google Sheet with you, but for this demonstration, let me just create a new Google Sheet and do it from scratch. So I'm going to start out, since this is for 7-dimensional basis vectors, I'm going to start out by putting the numbers 0 through 6 up top like this. And I'm going to put the numbers 0 through 6 going down the side like this. There's actually a way to do this. If I grab the handle and drag down, I'll fill this with 6s. But if instead I drag down while I'm holding the control key, they'll count up. So you could use that little trick if you want. Now, let's work the same way that I was working when I found my set of 5 basis vectors. Let's start out with all cosines. That is, in row 2, I'm going to create cosine of 0 theta. In row 3, cosine of 1 theta. Then cosine of 2 theta, 3 theta, 4 theta, 5 theta, 6 theta. So I can use the numbers here as my coefficients of theta. And I'm going to write equals cosine of, and then I click that cell, A2, times, and now I want my value of theta. And theta is going to be some multiple of 2 pi over 7. What multiple of the numbers in row 1 here? So I'm going to say this number times 2 pi over 7. Notice that pi is a function with 0 arguments. You type pi with an open parenthesis, closed parenthesis, and you get the number pi. So I actually have cosine of 0 times theta, where theta is 0 times 2 pi over 7, and then it'll be 1 times 2 pi over 7 all the way through 6 times 2 pi over 7. And that's how I get my cosine function. Now, that's a correct calculation for this cell. But if I drag this over to this cell, it won't work because my reference to this 0 is a relative reference. And I need this cell, when I fill this cell, to refer back to the number in column A, not a number in column B. Therefore, I need to put a $sign in front of that A. Now the way I've typed it will work for dragging it to the right, but it still won't work for dragging it downward, because this number B1 needs to refer to a number in row 1 only. Even when I drag it down to fill row 3, I have to refer back to the number in row 1. So I need a $sign in front of this 1 to hold that as an absolute reference. And I get cosine of $sign A2 times B $sign 1 times 2 pi over 7. And now that I've typed it that way, I'm free to drag the handle all the way to the right, and then drag the handle all the way down. And now I have 7 7-dimensional vectors. This is not my basis set because I've only used cosines now. And you can see, actually, if you just check in any one column, like column C, you can see I get 1, 0.6, negative 0.2, negative 0.9, and then they repeat, negative 0.9. The row starting with 4 is going to be the same as the row starting with 3. The row starting with 5 is the same as the row starting with 2, and the row starting with 6 is the same as the row starting with 1. And if I went to the row starting with 7, I would get back to 1, 1, 1, 1, 1, 1 again. So it turns out that these values, the rows starting with 4, 5, and 6, were redundant. I'm going to get rid of them, and I'm going to start in with the sines. And I'll take I'll start off with sine of 1 times theta and sine of 2 times theta and sine of 3 times theta, and I should get 3 new vectors. And by the way, now that I've changed that first column to 1, 2, 3, I can simply drag this handle down one box, and I get a formula in this box that's absolutely correct, except it says cosine instead of sine. So I'm just going to change cosine to sine, like that, and then I can drag to fill, whoops, I missed. I can drag to fill all the rest of the cells. Now, I have just created, right before your eyes, 7 seven-dimensional basis vectors, all of which are mutually orthogonal. When I handed you the six-dimensional basis vectors, I had them colored brown like that. So let me give them the same color. And you might be interested in checking your work and saying to yourself, are these vectors, is every one of these vectors really orthogonal to every other one? I don't encourage you to do that for the 12-dimensional basis vectors, because that would be a very tedious undertaking. You could do a spot check. But for 7 basis vectors, it's not that hard. The number of pairs of basis vectors to compute the dot product for would be 7 times 6 over 2, or 21 basis vectors. So here's a fun way. You could just check the dot products of 21 different pairs of basis vectors. The first, I could do the one from row 2 with the one from row 3. That starts out b2 times b3. And then if I drag that to the right, I'll get all the terms of the dot product, and I can add them up later. But first, let me just do the first term. Equals b2 times b3. Over here, I'll say equals b2 times b4. Oops. Over here, I'll say equals b2 times b5 equals b2 times b6, b8, and b7 times b8. So now I'm up to row 30. I started at row 10. Rows 10 through 30 constitute 21 rows. That's the correct number. Let me select them all. I'll drag them all to fill 7 columns. 1, 2, 3, 4, 5, 6, 7. Now I have all the terms and all the dot products equals sum of all of these. And then I click the handle here and drag down to calculate all of the dot products. And happily, I see that every dot product is equal to 0. So I've just demonstrated with 21 separate dot products that these 7 vectors are genuinely mutually orthogonal. I'm not asking you to do that part for homework. I'm just showing you for fun. Now, once you get the 12-dimensional vectors, I want you to go ahead and do what you did in this assignment, where you had a particular vector down here and you calculated the coefficients A for that vector. And the particular vector is going to be in the assignment. The instructions have a Google Sheet attached, so you'll all be working in your own Google Sheet. Just delete, there's a 7-dimensional basis set in the sheet. Just delete that and create a 12-dimensional basis set.